So let's do chapter 4.2. I think we can do all this at once. Chapter 4.1 was a lot of concepts, and it took kind of a long time. There's a lot to do. 4.2 is actually kind of short. A lot of it is kind of repeats various things that we've already seen before, and then 4.3 and 4.4 are also going to be a little bit heavy in amount of material. So they're just very, we just take one day at a time, and it's not so bad if you pace yourself. But this one's a little bit shorter, so we can do it kind of quick. So I hope this one is a little bit on the lighter side compared to its neighbors. All right, so we just want to talk about some graphs of polynomials, and we're going to have like a couple old concepts, a couple new concepts. And again, we're going to learn a little bit about what is and what is not possible for a polynomial to do. So it's just some of the basics for that. So one of the things that's sort of a new vocabulary, but it's kind of an old concept, is in this chapter, for polynomials, they call them turning points, but they're really just relative maximum and relative minimum from like a couple chapters ago. So just the polynomial goes up, and if it hits a maximum, and then on the other side it's increased, the function is increasing, then it's decreasing, it hits a maximum. That's a relative max. That's a relative extremum, and then that's one kind of turning point. The other kind of turning point is a relative minimum, which is the same thing as relative minimum. So just for some reason, the book sort of introduces this terminology right here, but it's really saying the same thing. And it's just a little bit of vocabulary. That's how it's written in the book. It's how it's written in the tests. So just that's really all there is to it. For polynomials, there's going to be, you can only have so many of them. There's a limit to how many you can have depending on the degree, and we'll talk about that closer to the end. But I want to just cover the basics, and then how many do we have of these things? We'll talk about that in a bit. So, all right, so here's just a picture of the graph. We just talked about the turning points. I put blue points, and then I circled them for the turning points. X-intercepts and Y-intercepts, those are kind of old concepts. I know we've seen those before. Let me just remind you. There are a couple new things to say about them, but mostly the definition itself is still the same. The y-intercept, it's really easy to get these confused. For the y-intercept, that means you're crossing the y-axis, which means x is 0. So when x is 0, that's where you have the y-axis. So it's x is 0 and it's the y-intercept. And the naming, it's if you're going too fast and you don't stop and think about what does the picture look like, you can get those two confused. So you're crossing the y-axis because x is 0, and then the y-intercept, well, if this graph is y is p of x, if that's what this graph is representing, then the y-intercept, that just means, well, you plug in 0 into the function, and then the y-intercept is the ordered pair 0, and then p of 0, or what, once you compute p of 0, you can just call it d, and then you can just write down 0d. Like if this is 4, 0, 4 is a y-intercept. All right, so just compute the function when x is 0, and that's the y-intercept. So that's pretty straightforward. Turning points, for now, the only way you're going to figure those out is by having a very good graph to look at. For parabolas, that's the vertex. That's a very special case. Usually, for anything more complicated than a parabola, you probably need to use calculus. So for now, just graphically, if you have a really, really good graph, yeah, I know where the turning points are. My computer computed the function thousands of times and in a matter of seconds, and I got a really nice graph, and there it is. So that's that. So we got y-intercepts the turning points, and then x-intercepts is the opposite. That means y is 0. So this is what we talked about, zeros and multiplicities. X-intercept is ordered pair. So x-intercepts, there might be none whatsoever. There might be several. There might be just one. If it lies on the graph, that means, oops. You're going horizontally along the x-axis, but then the output of the function is 0. So you go along the, here's where you cross the x-axis, that means y is 0. Or in this case, in this picture, there are 3 of them. And it's and this graph is meant to represent the entire, this graph is meant to be more or less complete in the kind of overall representation. So if it were to turn around again, it would be customary to draw a bigger graph that includes that. But if it does this, this, and this, and then it keeps going, then we've got the end behavior, and that's basically the main features of this picture here. So, all right, so what I want to do is I want to summarize for each of these 3 concepts, how many of them can we have? So let me do that on the other side. So a polynomial, the domain of a polynomial is just all real numbers. There's you can always plug numbers into a polynomial, because the polynomials, by definition, you're just taking powers of x and then multiplying by some given coefficients, and that's no big deal. It just works all the time. And you plug in 0, and that's when you plug in x equals 0. That tells you where the y-intercept is, and there's just the one. All right, so we have x-intercepts. And let me, I think the book uses in. So sometimes they use d for the degree, but the book usually calls it in. And dot dot dot. I guess if I'm continuing the sentence, I should use a lowercase. And there's a technicality here. Constant functions, actually, the 0 function could potentially, the 0 function either has no x-intercepts, which would be fine, but the 0 function is technically a polynomial, and every single point on the 0 function is an x-intercept, which would be kind of goofy. So we're not going to worry about that too much. We don't really, the whole point of this is we want to understand degrees that are, at least 1, 2 we already kind of understand, but 3 and higher might be tricky. So let me just do a quick sketch of this. So like just for parabolas, for example, how many x-intercepts does a parabola have? That's like y equals x squared. But here, this is like y equals x squared plus 1. Even just by adding a constant, we here we get exactly 1 x-intercept. But if we do another graph, you can either see it from the graph, or you could actually solve for that. If x is plus or minus 1, we get 2 x-intercepts. So no x-intercepts. 1 x-intercept. So it's just, you're not going to have more than 2 for a parabola, because it can open up or it can open down, and then either you're completely on one side of the x-axis, or you just barely touch it, or you cross it twice, going both ways. But in general, this says that ax cubed plus bx squared plus cx plus d has 0, 1, 2, or 3. It might be one of those numbers. It turns out just because of in behavior, odd degree polynomials have to have at least 1. That's kind of an interesting fact, but in general, we just need to remember that it has to be one of those, and then for 4th degree, maybe it looks like a parabola again. You have 0, 1, 2, 3, maybe in 4 for a 4th degree, and so on. So it just depends on the polynomial. There always exist polynomials that have exactly n zeros, and there are always polynomials that have fewer than that. For like higher degrees. So, all right. So the reason for this, by the way, is you can factor them out by long division. If x equals 2 is a 0, you divide the whole polynomial by x minus 2. X minus 2 factors out, and then whatever's left over, you factor it some more. And how many times can you factor it? Well, you can only factor it. You can only have as many x's. You can only have so many x minus c factors as there are, the highest degree of x. You just can't, once you factored it all the way down to linears, you can't go any farther. So that's the cool thing about polynomials. And this is the last one that it's kind of basically the zeros and the multiplicities stuff that we did. So we have a times, maybe there's an irreducible, but then we have x minus c1 times x minus c2, and so on. So we have these zeros, c1, c2, with multiplicities m1 and m2. Just the previous video basically explains why you just factor, and eventually everything that could make the function 0 ends up in one of these. And the last one, a polynomial with degree n greater than 0 has at most n minus 1 turning points. So this is similar to zeros, and it's actually it's kind of a very, very closely related fact. don't want to say too much about this. It's a fact that you want to memorize now. Just it's a nice thing to know. It's one of the most important properties about polynomials. So a parabola is a second degree polynomial, and there are exactly 2 minus 1 turning points for a parabola. So exactly 1 for a parabola. So that's kind of interesting. Let me just do an illustration of a few cubic things, and then we'll sort of see a little bit here. But that's roughly the idea. So third degree, let's look at turning points. I just want to give an illustration. This is not a proof. This is just one example. And like, yeah, the bigger the degree is, the more complicated things can happen. The different terms can interact with each other, and that's cool. But let's look at y is equal to x cubed. Let me just give a quick graph of that. This is one you should already sort of be familiar with. It looks kind of like this. Yeah, technically there's like 1, 1, and then there's 2, 8. So something like this. So this one, it's increasing, it sort of turns flat, but then it just keeps going. So there's no... So y equals x cubed has no turning points, but here's one that does. So y equals x cubed minus x. Now that one's a little bit interesting. When x is plus or minus, yeah. When x is plus or minus 1, this function is equal to 0. So it actually hits, so it has 3 x-intercepts. And that's really interesting because it has a similar shape, but in the middle it does this. In calculus, you'll actually learn how to find these x values. There's actually, you just gotta, if you're really super duper interested, you can tough it out for a few more semesters and learn all about this. But this is a very nice calculus problem. If you learn your algebra really good, and then you'll be ready to do this too. But this one here, well, if you just have a graph, and so 1, 2 turning points for this. So this cubic has no turning points, so it's possible to have less than 2, but there's no way you have more than 2. If you want more than 2 turning points, you have to cook up some 4th degree, 5th degree, 6th degree. If you want more turning points, you need a polynomial with higher degree. And I don't know, if any easier, by far the easiest way to prove this is with calculus. And if you don't have calculus, well, calculus, you do a lot of work, but then you get a lot of stuff. There's a lot of payout. You put in a lot of effort. It's like, it's like building a computer. It's like a computer, learning how to use a computer is a ton of work, but then you get to check your email. You can call people on FaceTime. You can do all kinds of things. In calculus, this is just, it's by far the easiest way to prove this fact about polynomials. If you were to graph lots of polynomials, take lots and lots of data points, you would maybe start to suspect that this was true, but the most standard proof is calculus. So So let me just say a couple of things. This is kind of like your homework, but let me just make sure that it's something different. Let me just erase the right-hand side, and I just want to okay, so something like that. So what can we say about P? Degree equals 10. P has degree 10, 1 y-intercept, x-intercepts are the ordered pair on the graph, and then the x value of that ordered pair is called the zeros. So at most 10 x-intercepts, at most. So the zeros are just the x value. The x-intercept is the ordered pair thought of as something that's on the graph. So they're kind of the same information, but kind of formatted a little bit differently. Most, not 10, but 9, because it's n minus 1 is equal to 9 in this case. So the number of turning points, I mean, a parabola is second degree, but there's only one turning point. Same thing with the cubic. It's third degree, but that example only had 2 turning points. You can never get more. This one is 10th degree. Maybe it has 9 turning points. It probably has less, but it could have 9, for all I know. And it's gonna alternate between like max and min. So we could have like 4 max and 5 min, or 5 max and 4 min, something like that. That's kind of it. That's really all we want to say here. We could also, put it all together. We can talk about in behavior. So this one, you can ask the usual questions, because 4.1 and 4.2 are kind of very related. They have some overlap. So what is this polynomial going to do? It's going to go up on the far left side. It's going to go up on the far right side, because it acts like an even power of x with a positive coefficient. But in the middle, there's a lot of chaos. Well, not too much chaos. It can only go down and then up again. It can only hit 9 turning points total. Probably fewer, but it might hit 9 of them. It might cross the x-axis 10 times, but possibly fewer than that. And it's going to cross the y-intercept. And that's it. That's kind of everything. Hopefully this one was not quite as tricky as 4.1. I think 4.1 we legitimately had some work to do, and this one, it still worked, but I think less so. But yeah, so let's see how it goes. I think that should be good.